So my voice is audible to you all?
Yes,
Yes,
ma'am.
Okay. So in the last class, we have studied about the graph traversal algorithms. So BFS and DFS. So now we will study the shortest path algorithms related to graph. Now, this shortest path algorithm means that given a graph or given an image, we will calculate the shortest path between the nodes or the vertices of the graph. So several type of algorithms are there. First one is the famous, which you have heard, is minimum spanning tree. Under this minimum spanning tree, we will read two, which is in our syllabus. One is the Prim's algorithm and another is the Kruskal's algorithm. Fine. Next algorithm in order to study the shortest path is Distract's algorithm. And the third one is either Warshall or Floyd-Warshall, whatever you may call it, Floyd-Warshall's algorithm. Okay. So these three majority are the types of algorithms through which we find out the shortest paths given any graph to you, the shortest path between any vertices. Fine. Now, this minimum spanning tree and this distress algorithm, they use the concept of adjacency list. We have studied that two types of representations are there. One is linked list and another is matrix. So these two types they use, or this algorithm is generally executed in the concept of adjacency list, and this Floyd-Warshall's algorithm, this is generally executed in the context of adjacency matrix. Actually, the type of logic is there in this algorithm. This forces to be done by adjacency list, and the type of logic in Warshall's algorithm, this forces it to be run with the help of adjacency matrix representation. Fine. Now, first we will start with minimum spanning tree. I am writing in short MST. Now, what is this minimum spanning tree? So, it's a tree of connected undirected graph where it is like a tree where all the vertices are together. They are connected by some edge or the other. And one graph may have any type of tree. Suppose if I have, this type of vertices. Suppose this is the graph which is there. Fine, this is the graph. So one tree can be like this. Fine. Another tree can be like this. Fine. So lot of representations of the same graph can be there. This can be one spanning tree. This can be another example of a spanning tree. So spanning tree concept is the nodes or the vertices that are there, they must be connected to each other by some edge or the other. There should not be any such case like this. This node is not connected. This should not be the case. So given a graph to you, different spanning trees can be there for the same graph, and within these different types of spanning trees, we find out the minimum spanning tree. Now, how do we find out the minimum spanning tree? by seeing at the weight that it assigned to each edge. Because we know we assign weights to each edge, and the weight we assign, we can use this in order to calculate this. Suppose this is the weight I am assigning to this this graph. So this would have been fine. 4 plus 4, 8, 8 plus 3, 11. This spanning tree's weight would have been 11, and this spanning tree's weight would have been 6 plus 4, 10, 3 plus 1, 14. So as you can see, by assigning the weights, we have different values of the spanning tree. Now, if I ask you which is the minimum out of this 2, 1, obviously this 11 is minimum, that this 14. So if asked to represent it as a minimum spanning tree, I will obviously choose this one. But it is being simple because the graph is simple. When more and more complicated vertices or a huge number of vertices or huge number of nodes comes into existence, then we cannot do it verbally, right? We will have to follow some logic, so that that logic applied for infinite number of nodes also, it will run and it will give me the result, right? So this was the concept of finding out the minimum spanning tree from several spanning trees of a graph. So by calculating the sum of these weights of these edges, we get a value which will help us to find the minimum spanning tree. So now when asked what is a minimum spanning tree, the answer will be that it is basically a spanning tree with the weights which will be less than or equal to the weight of every other spanning tree of that graph. So that is the minimum spanning tree. Fine. So out of the several spanning trees, the weight of that particular spanning tree, which will be less or minimum, will be called as our minimum spanning trees. Now, what are the applications of this minimum spanning trees? They can be used for designing the networks. They can be used for airline routes. They can be used in order to find out when we have to connect several cities, computers, via roads, airlines, airways. Then we cannot do it physically, right? We will have to abide by a concept. Like this much distance between any two cities, how much of length of wire would have been required if I follow this route, or how much of wire will be required if I follow that route. So for this type of decision making, it comes into help. Fine. So for routing algorithms, like in computer networks, when we study about networks, we study that this information goes through the wires. It reaches from one computer to another over a network in the form of packets. So out of all the IP addresses, exactly how come it is locating the IP address of the recipient? So they need to follow some routes in order to do that. These are termed in our computer as routing algorithms. Now for implementing these routing algorithms, these concepts of graphs, spanning trees, minimum spanning trees comes into existence. Okay, so up to this one, what I was saying about this minimum spanning tree, is it clear to you?
Yes, ma'am.
So under this minimum spanning tree, two types are there. So first one is the Kruskal's algorithm, next is the Prim's algorithm. Fine. So Kruskal's algorithm will find the minimum spanning tree of connected weighted graph. Fine. So what does this algorithm does? Suppose you are given a graph. This algorithm will find the subset of all the edges. Suppose A, B, C, D. These are the four nodes. And there is one edge AB, another edge AD, another edge BD, another BC, another CD. So this type of 5 edges are there in this particular graph. So what will happen is, since every edge will be associated with a value of that edge, with a weight of that edge, it will first sort the edges according to ascending order of their weights. Suppose A to B has 6 weight and B to C has 1, this is 2, this is 3, and this is 7. Suppose. So what will happen is, first it will store BC, then it will store CD, then it will store BD, then it will store AB, then it will store AD. So like this, according to the ascending order, lower to higher edges it will store. According to the weights, the edges will be stored. Then what happens is, out of these edges, this algorithm will try to build the tree such that every vertex is connected, but every vertex is connected according to the minimum edges, and ultimately when I will connect every vertex according to the minimum edge, I will get a minimum spanning tree. The weight of my tree will be minimized. So the graphs or the edges that will be connected according to a minimum spanning tree concept. Now I will just take one example and then show you, maybe that will be easier for you to understand. Okay, so this is the graph which is given to you, and these are the several weights that are given to you associated with this graph. You are asked that apply the Kruskals algorithm on this graph given to you in order to find out the minimum spanning tree using the concept of Kruskals algorithm. Now, 3 things need to be noted. When I will create a minimum spanning tree, it will be definitely a subgraph, not my entire connected graph. So first, what will be present? All the vertices need to be present, and the vertices need to be connected with the help of edges. Fine. And there will be no cycles. If in adding any edge to my subgraph, I see that a cycle is forming, then I will discard that edge. So no cycles should be there. And after maintaining all this, I will do the summation of the weight of all the edges. The summation I will get, that will be of minimum value, and the byproduct, that is the subgraph of that I will get, that is the minimum spanning tree for that graph using the concept of Kruskals algorithm. Fine. So this is the concept. Now, what did I say? I said that we will keep on including the minimum edges as long as no cycles are found. And if any cycle are found, we will stop there. And if once we cover all the vertices once, one at a time, that is all the vertices are connected for once, we will immediately stop there. Now, if that is the case, the first logic which I need to apply and do is I will have to sort all the weights according to their ascending order. If I do that, several values are there: 1, 2, 3, 4, 2 times 5, 6, 7, 8. Right? So the edges and the weights. So weights are 1, 2, 3, 4, 2 times 5, 6, 7, 8. These were the ages, and the ages associated with was AD, EF, CE, DE, DF, CD, AC, AB, and BC. Did I cover it all? 1, 2, 3, 4, 5, 6, 7, 8, 9 values. 1, 2, 3, 4, 5, 6, 7, 8, 9 values. Fine. So I covered it all. I will just erase this part. Okay. So can anyone please say which is the first age which I should consider? Oh, first how will I build the thing? First, I will draw all the vertices. First, let me just draw the vertices. Fine. So what is the first age which I will include? Anyone? The first age which I will include?
AD.
AD. Since it's 1. Next age which I will include?
EF.
Since it's 2. Next age which I will include?
CE.
Next age which I will include?
DE.
Next age which I will include? Now, I will not include DF because even if it is 5, it will lead to me a circle. If I include this age, it will give me a cycle, right? So I won't be including this age. Again, if I include this age CD, then also it will give me a cycle, right? CDE, in between there will be a cycle, see? So even if it is 5, I won't be including this age because we will have to avoid cycles, right? Next, I will go to AC. If I go to AC, will I include AC? Yes or no? Anyone, will I include AC?
No, ma'am.
And why I should not? Because again,
Ma'am, from cycle from current.
ACED, it will be a cycle, right? So I won't include AC even if it's 6. Then remaining is AB. Should I include AB? Yes, I may include AB. Right? Fine. Should I include BC, or even do I need to include BC? I do not need to include BC anymore. Why is that? Because the reason is, if you notice, all the nodes are connected in some way or the other, right? So I do not need to include BC anymore. I do not need that in my process. Up to this step, by following this step, all the nodes are connected with some edge or the other, with the other vertices, right? So my MST is already done. I do not need to include any more edges. So what is the finally the summation of the weight of my edges? Summation is 1 plus 2 plus 3 plus 4 plus 7. So 2 plus 1, 3, 3 plus 3, 6, plus 4, 10, plus 17. Fine. So this is my resultant minimum spanning tree pertaining to this graph, applying the Kruskal algorithm. And this is the value of my minimum spanning tree following the Kruskal algorithm. Anyone has any query in understanding this? Did you get it? How we did that?
Yes, ma'am.
So now let us study the next algorithm under the minimum spanning tree, that is the Prim's algorithm. Now, Prim's algorithm also gives us the minimum spanning tree, but for connected, weighted, undirected graphs only.
Ma'am.
Yeah.
Ma'am, please, will you please show the previous page, ma'am?
Yeah.
That summation one.
ठीक है? ठीक है?
Okay, ma'am. Thank you.
Okay, okay. अच्छा.
Okay.
So, अभी हम लोग पढ़ेंगे क्या? Prim's algorithm. Now, Kruskal's algorithm, they works for connected weighted graph. Prim's algorithm also works for connected weighted graph, but Prim's algorithm only works for undirected graph, whereas Kruskal's algorithm can work for any type of graph, be it a connected, be it a weighted, directed, undirected. This is the slight difference. Fine. So Prim's has one limitation. It only works for undirected graphs, but whereas Kruskal works for all varieties of graphs for minimum spanning tree founding, in order to found the minimum spanning tree. Now, Prim's algorithm, how does this works? We will explain it with one example. Otherwise, it will be very difficult for you to understand. Let us jump to the example. Then we will discuss that. Let me just draw the graph. Fine. So this is the graph given to you. Now what is done in Kruskal's algorithm is, first we will avoid all the self loops. If there are any, we will avoid the self loop. Self loops means a loop like this. If there will be anything like this is known as self loop. Vertex starting here, ending here with weight something. We will avoid it. If there are any, we will simply chuck it out. And we will avoid parallel edges also. Suppose between A and D there is one edge, and between A and D also there is one edge. So we will not keep all the parallel edges. The only lower in value parallel edges we will keep. So suppose this is the 4. If this edge would have like this, then I would have kept this weight only. So parallel edges will be discarded. Only the one with the lowest edge will be kept. So earlier my graph was this. So this is the lower edge. So I kept it like this. Okay. So 2 rules are there. First rule is avoid self loops. Second rule is avoid parallel edges except minimum. We will keep the minimum edges, right? So if the number of vertices in my graph is n, then the number of edges for the spanning tree will be n minus 1 or something, right? So if there are edges between any two vertices, we will mark it with the value given to it. And if there are no edges between any two vertices, I will simply mark it as infinity or label it as infinite or any symbol you want to give, which will imply that there are no edges. Fine. So given these are the conditions, first, let me draw the list. These are the since we are avoiding self loops, so any F to F, A to A, all these edges will not be there. So simply the diagonal elements will be all zeros. Since A to A, B to B, C to C, all no self loops. So we will simply put zeros, and next we will fill up this entire vertex as A to B, there is 2. A to C, no connection. So if there is no connection, infinity. Then A to D, the connection is there 4. Then A to F, there is a connection with 5. And other two, there are no connections. So like this, we will fill up the entire matrix. So similarly, between B to A, there is a connection. Between B to F, there is a connection. Between B to E, there is a connection. Between B to C, there is a connection. Between B to D, there is a connection. Between B to G, there is a connection. Fine. So if connections are there, we will put the value. If no, we will put a 0. Clear? So between C to A, there is no connection. Between C to D, there is no connection. Then the connection is between B, then E, and then G. F also is not connected to C, right? So like this, I will just quickly fill up all my So this is my entire connection. Clear? Now what I will do, I will follow edges by edges. Now I will go edges by edges. So if I first see this row, I will start with the first row, and row by row I will go. And the concept is I will select the minimum from that row always except 0. And that falls in which column I will have to check. So the minimum from this first row except 0 is where? Anyone? The minimum from this.
Please.
The minimum from this row.
Please.
Ma'am, A to B.
A to B, right. So this is the minimum from this row, A to B, right? So I can first draw like this, A to B. Second, when A to B connection is there, the column which included is B. Now I will look for the minimum combining these two rows. So if I look for the minimum combining these two rows, where is the minimum value?
B to D, ma'am.
B to D, this one. So I will take this one. Now, since D is the column which is now involved, now A, B, D I will look. If I look at A, B, D, which is the minimum value?
D to B, ma'am.
But that is already there, so I won't see. Next, which one is the minimum value?
E to E.
D to E
E to E? Yes, I will take.
or B to A.
No, B to A I cannot take.
Yes, ma'am.
So D to E. Fine. Now I have another column E. Now A, B, D, and E. Among these 4 rows, which is the minimum?
E to D.
Ma'am,
E to D.
E to B, ma'am.
But can I include E to B?
No, ma'am.
No, ma'am.
Circle हो
Then
जाएगा.
next one, which is the minimum?
E to D.
E to D is already there.
Ma'am, E to C.
E to C is minimum. 10, wait. Between 2, 3, 4, 7, 8, 5, a lot of varieties are there.
Ma'am, B to C.
B to
C.
no. B to C is 7. Can't you not see B to G, this one? 4. 4 is a minimum value.
Yes,
Na?
ma'am. Yes, ma'am.
So I will include this B to G. Then G column is involved, right? So A, B, D, E, G. Between all these 5 rows, which is the minimum?
G to F.
G to F.
G to F.
Perfect. Then between F, A, B, D, E, F, G, which is the minimum? G to C.
Yes,
This is
ma'am.
the minimum. Now, and if you see as an output, A, B, C, D, E, F, G. All your vertices are connected with each other. And the weight is 2 plus 2, 4 plus 1, 5, 9, 10, and the weight is 16. So this is your minimum spanning tree following Prim's algorithm on this graph. We'll just quickly share the attendance. Okay, so those who are from this college, please mark your attendance over here. And if you are from other college, you can write your name hyphen your department in the chat box. So while marking the attendance, just let us revise. Did you understand the Prim's algorithm, how it worked? If we will start with the first row, and for each and every row, the column which was selected as the minimum, that named row we will also include in our next search. So first A, we search row A, then B column, under B column we saw there was a minimum. Next we will search for minimum between A and B. Then we saw D column is getting minimum. Then we will search for the minimum between A, B, D. Then we searched for the minimum between the rows A, B, D, E. Then we searched for minimum. So like this we go on. Okay. So this is the logic. And at first we do what? The places that are not connected, we marked it with infinite symbol. You give any symbol. And the places and the self loops need to be avoided. So all the diagonal elements will be 0. So A to A, B to B, C to C, D to D. All the self loops will be 0. So first these 2 things we will do. And next row by row, according to the columns that are selected under the rows, we will include column by row by row. So first we will including row 1, row 2. Then we will include row 1, row 2, row 3, find the minimum. Then we will include row 1, row 2, row 3, row 4 to find the minimum. Like this we go on till all the vertices are connected with some vertex or the other with the help of a weight. Okay. So this is the logic. Now, in this Prim's algorithm, I started from the first row. Sometimes in your exam, they specify that take, suppose apply Prim's algorithm on a particular graph and start from vertex B or vertex D. So they will tell you from where to start sometimes. So you start from that vertex thinking that is your row 0. You start from vertex D, that means row of D. There you find out the minimum. Look for which column it falls under. You club that 2 rows next in order to find out the minimum between that 2 rows. And you go on doing that. So there is no hard fast rule that you will have to start from row 1. Whatever the question is, if they ask you to do from some other vertex, you start from that row which is named at that vertex. Are there any query regarding the Prim's algorithm?